Hello, and welcome to this video where I'm going to go through and debrief the first exam for the spring 2024 semester. So what is the main purpose of this video? While I will walk through each individual exam question, the main purpose of this video is to help you see how the various elements of the course fit together. How the textbook prepares you for the homework, which prepares you for the quizzes, which prepares you for in-class, which prepares you for the exam, which brings us to where we are. If after watching this video, you still don't see how all these different pieces fit together, please, please, please make an appointment to come and see me. So before we get in, a few comments from the post-exam reflection that I particularly wanted to address. In big picture, there were a lot of pieces and tools. This is something that came up a lot in the reflection. And I recognize that, yes, this course does have a lot of pieces, and that can make it confusing and complicated. But the reason is because I'm trying to provide as many resources as I can to help you be successful, which means there ends up being a lot of stuff. So it's definitely a give and take. There's definitely some tension there. The second biggest overarching comment was that the structure is very different from what you're used to from prior classes with regards to the homework coming before what we talk about in class. And finally, that the aim of this class is different. That, yes, there is an effort to learn facts, but that happens in the homework, that happens in the quizzes. But what's really being tested on the exams is a skill, your ability to apply these concepts to a new situation. So let's begin with a representative example of the most common comment, which says that homework is sort of disconnected from the stuff we go over in class, and you have to read the book to understand anything that is happening in the homework. Coming to class does not help you do the homework at all. Maybe, presumably me, should teach some of the concepts that is going to be on the homework in class, so class doesn't feel as irrelevant to the work we do outside of class. So this comment is really sort of getting at to the core of a question of what is the point of the homework? How does it fit in with what we are doing in class? And so let's return to the very first day of class to sort of remind ourselves of what we're doing and why. So on the first day, we talked about what physics is, and that the goal of physics is to uncover the fundamental concepts and rules which govern all the processes in nature, right? And that we then want to apply those rules and use them to learn new things, to gain new insights into how the world works. And that this dictates how we are going to study physics. So we see there's two bullets, the fundamental concepts and the application. The fundamental concepts are your homework, right? This is, just as the comment said, out of the book. Yes, I am asking you to get some of this conceptual information out of the book and the other resources that are available, the Discord, the Help Center, all these types of things. I am expecting you to get that information from our textbook, right? So, and then the quiz is to make sure that you actually did get that understanding. We then use that understanding. We use those fundamental concepts that you explored in the homework in class to practice applying these ideas, gaining insights, practicing the skills, learning techniques, which we then use on the exams. So that's the model. And so in a sense, the comment is 100% correct. I am going to ask you to learn the stuff for the homework from the book so that we can then use class time to apply that fundamental information to problems in class and learn how to solve problems together, right? So let's look at Unit 1 sort of as an example. One of our last problems in Unit 1 was, what does the Earth get from the sun? This was Unit 1, Day 8, Slide 10. So one of the very last days of Unit 1. If you wanted to do this problem, you need to know the mathematical definition of entropy. You need to, I mean, the whole thing is basically coming down to the difference in entropy between the incoming sunlight and the outgoing thermal radiation from the Earth. In order to understand that, you need to know what entropy is. And that was on Unit 1, Day 5. Really, Unit 1 started with day 5. There were really only 3-ish days of Unit 1 when you think about it. And that's because I had to wait for y'all to finish your Unit 1 homework to get that understanding. But in order to understand what entropy is, you need to be able to count combinations, because entropy is the number of combinations, as we discussed on Unit 1, Day 5, Slide 14. And so there was a quiz problem which tested your ability to calculate combinations based upon, so that we could then use that to describe entropy. Well, if I'm going to test you on your ability to determine combinations, I should really give you some practice for it first. So I did. There were several homework problems that sort of helped you develop the skill on learning to count combinations. One of them was homework problem number 8, where you looked at the NFL division playoffs, right? Where were you supposed to get the information for doing this? Well, in order to count combinations, you actually needed some basics of probability, which was homework problem number 3, and an or in probability. Well, where were you supposed to learn that sort of stuff of and or with regards to probability? That's where your book came in. Chapter 4. There was this video of and or in probability. So you can see that, no, we didn't use the stuff from the book and from the homework necessarily explicitly in this last problem about what does the Earth get from the sun. We used it implicitly. It served a foundational purpose. You wouldn't have been able to approach this problem of what does the Earth get from the sun if you didn't have all of this other information that came before it. So this is how the course all sort of fits together. Another common comment was regarding the in-class practice. I wish the instructor would walk us through the first problem step by step and explain the process of each step so that there's no room up for debate on what we're supposed to be doing. This is sort of a representative comment of a theme that was brought up a lot. And I'm going to counter that I did, right? So you can see here an example, the summary of the example, the first example problem I did when it came to energy. And I've added a few extra comments here on what was going on. And you'll note these are general procedures, but these procedures apply to any problem in our energy unit. Every problem works this way. Now, I know some folks are asking or have in their mind more specific series of steps. They're looking for, how do I solve a diffusion problem? Or how do I solve a polymer problem? Or how do I solve, the pencils in the box problem? And what I'm going to push back is, these are not different classes of problems. These are all entropy problems in the exact same way that, the syringe where I set the cotton on fire, or the crushing can, or the roller coaster are all different energy problems. Your goal is to get to that point where you see all of these problems as being just manifestations of the same underlying process. So a few other comments. I wish the instructor covered more test-related content in class. And as we will see throughout this video, the in-class problems are very intentionally preparing you for the exam. In fact, I wrote the exam first and then wrote the in-class problems afterwards to ensure that there was a mapping between what we did in class and what was on the exam. And of course, in line with the physics is about learning to apply new concepts, the problems are not the same to the ones we did in class, but the techniques and skills are very much the same. A couple people asked effectively, what am I supposed to get out of each class? There was a couple comments along this same sort of vein. Primarily practice with the problem solving skills. However, the broadcast, the emails I send out have a very concrete description of exactly what I want you to be able to do at the end of each class. You can also find this information on Moodle, where you go and download the slides. There's a blurb there at the top that has bullets for each individual day of exactly what I want you to be able to do by the end of every day's class. The last comment was that there are rarely any chances I can practice or review material outside of class, except for the notes, which this particular person apparently didn't find very helpful. Similarly, posting weekly optional problem set would be helpful. These exist. You have the next time problems at the end of almost every day's class, and you have the additional practice worksheets for each unit that have been up since the beginning of the semester. As we'll discuss in class, those who said that the additional practice was a lot of their studying on the exam reflection did significantly better, 11 percentage points, than those who didn't really use this particular resource. So why is it done this way? Why don't I require it? Because I think this course already has a lot of required elements, right? The prep is not short. There's the lab, which is not trivial either. There's a lot of pieces to this class, and I'm reluctant to add more required material. So instead, I'm giving you a bunch of resources and saying, y'all are smart, y'all are competent, y'all have been around the block a few times, y'all know what you're doing. Do what you need to do. That's the whole sort of philosophy with the end of chapter. It's because I don't want to overburden you with a bunch of busy work that you may or may not need to do. The other reason for doing it this way is because there comes a point in life where people stop teaching you things. For example, my PhD is effectively in statistical writing computer software to writing computer software to do statistical analysis of large data sets. It says particle physics, but that's really what it is. And I have never had in my life an exclusive computer programming class, nor an exclusive statistics class. It's kind of weird that physicists don't have to take stats, but we don't, right? So a huge part of it was self-taught. You know, when it comes to stats, I consider myself a proud graduate of the University of Wikipedia. Like, people stop teaching you things. And I'm trying to prepare you and scaffold you a little bit for that experience. I'm giving you the resources to say, okay, these are the things that might help you prepare for the exam. Use them if you need or not. You know, y'all are smart. Y'all can do this. So now I'm going to move on and actually start to tackle the individual exam problems. And I want you to, in particular, not just pay attention to the solutions, right? You're not out to collect solutions to every problem. These problems are not going to be on your next exam, right? It will be new ones. I want you to think about how it connects to what we did in class so that you can then build on that expertise for our next exam and maybe, if you would like, be a little bit more successful. So let's start with problem one here. So you had this block at the top of a hill situation, and you were out to solve it, right? So the first part was, what types of energy does the block have initially? Well, it's at the top of a hill, so it has some gravitational potential energy, and there's a compressed spring there, so it has some elastic potential energy. There's no kinetic energy because the block's not moving. There's no change in chemical energy. There's no change in thermal energy here that's going to be relevant for this problem. At the end, all you've got that's relevant for this problem is the gravitational potential energy. So you'll notice that there are multiple parts here, and that's so that basically I can give partial credit. If this were a smaller class, I might just give this problem as an open-ended problem and ask you to just solve it out on a piece of paper. That's actually what I've done for smaller classes. But given the size, that doesn't really work for this class. So I've broken down what I would have given partial credit for and written separate questions. Moreover, it's explicitly testing that idea of write me a story of how the energy is moving through the system, which we spent time on in class. And I explicitly said that, you know, I would test you on your ability to write an energy story. And so that's what these first two questions are doing. For the third part, which gets into the math, you know, we could solve it out. We've already established our story. I start with gravitational potential energy and some elastic or spring potential energy at the beginning. And I end with gravitational potential energy and nothing else. So that's me translating the story of parts B and C into a mathematical representation here. And then I can go and put my definitions in. So gravitational potential energy, well, that depends on mass, the planet I'm on, and the height. The spring potential energy depends upon, there's a 1/2 from your reference sheet, the stiffness of the spring in question, and how much it has been deformed, with deformation being more important, so the square. And then I have my gravitational potential energy here at the end. Then I can go and do some algebra on this. I am solving for x. So I'm going to begin by moving this MGHI over to the right-hand side there. I'm going to factor because I like to. Bring this 1/2 k xi squared along for the ride, and then multiply by 2 and divide by k. So that gives me a 2mg over k hf minus hi. Now when I go to put numbers in to this is where the numbers, each person had different numbers here. So the mass of the block was 1/2 kilo. G, assuming we're on Earth, is 9.8. K was 116. HF was 6.5. And HI was 5.5. And that was xi squared. And when you go and solve all that out, you get, for this particular combination of numbers, 0.2906 meters is what I get for this particular combination of numbers. How does this relate to what we did in class? Well, Unit 1, Day 3, slides 12 and 13, the roller coaster, was almost an exact replica of this problem, particularly Part B, where you were looking at how much, what stiffness of spring do you need, right? So take this one and instead run it the other way, solve for k instead of solving for x. It's the exact same problem as this roller coaster. There were very similar ones on Unit 2, Day 4, slide 14, where we had this, what ended up being the oxygen molecule puzzle piece on the track, and these 2 pulleys from the Unit 2, Day 3 to Day 4 next time problems. All of these were transferring macroscopic forms of energy, springs and gravity and that sort of stuff at the macroscopic scale here, in a closed way, where there was no energy, gained or lost from the environment. So problem 2, we'll start with this first part, Part A. What is the entropy of subsystem A? So for that, we're looking at entropy. So we know what entropy is. It's KB ln of W. So I need to think about, what is W? W is the number of combinations. So in A, I have 6 flames and 8 slots. In other words, W is 8 choose 6. It's 8 choose 6. And when you go and you calculate out what 8 choose 6 is, you'll determine the correct answer for this problem. This is exceedingly similar to our problem we did with regards to energy in a box in class, and also the polymers. So we had these polymer folding, right? Binary entropy, combinatorics, all that sort of thing. The oil and water was also a combinatorics problem, very, very similar. So you can see on the left here, you had 12, 6, 6, 6, and 6. 6 times 4 is 24, plus 4 is 28. So you had 4 waters in 28 slots. So very, very similar. So this was 28, choose 4, whereas this was 8, choose 6. So very, very similar in that regard. And also our sunlight problem was exceedingly similar. And then, of course, we had actual flames in buckets on Unit 1, Day 8, Slide 13. When it came to problem 2, thinking about how W and S combine together, well, we did this exact problem on Unit 1, Day 5. So slide 11, we looked at how microstates combine. We found that they were multiplicative. And on day 5, slide 12, we concluded that entropies had to add. And then on slide 14, we used this information to determine what the mathematical representation of entropy was. And so from there, we conclude that microstates multiply and entropies add. For part C, the question was, how many packets do I have to move from A to B to be in the highest entropy state? Well, this is almost a direct version of Unit 1, Day 8, Slide 13. You can see this was 4 and 8 instead of 6 and 6. So the exam question had 6 slots on both systems, whereas the one we did in class was uneven number of slots, but same basic idea. And when we solved that through, we got the actual answer on slide 14. And that was that they had to come to the same temperature. The energy per degree of freedom had to be the same in both systems. So in order for that to be true here, I need the number of flames divided by the number of slots to be the same in both system A and B. And the way to do that is to move 2 flames from A to B. And now you see that there are 4 in each. And that will be our highest entropy state. You could have also just started moving flames from A to B and seen how the entropy changed. If you moved 1, the entropy of the system would go up. If you moved a second, the entropy of the system would go up again. And if you moved a third, the entropy would go down. But this, I thought, was probably the easier way to approach this particular problem, was more of a conceptual understanding. Problem 3 was our arm problem. So this is getting to the idea of center of mass. So we know that center of mass is a mass-weighted average position of things, of all the things I've got in my system. So in this case, we know that the forearm is 10 centimeters for center of mass and has a mass of 1.14. The hand is at 28 centimeters with a mass of 0.45. And the denominator would be the sum of the masses. And when you go and calculate that out, I got 15.09 centimeters when I went and calculated that out. Very similar to this 2D problem that we did in class altogether on Unit 1, Day 3, Slide 12. Unit 3, Slide 15, I actually did the full arm, not just the forearm. I did the full arm here, and at least talked about how to set it up. And then you were to go and solve it on Day 3 to Day 4. That next time problem, Unit 1, Day 3 to Day 4, is when you were supposed to go and solve that problem. And you can see that that's just sort of an extended version of this particular exam question. So if you had done this next time problem, you were probably pretty well prepared for this particular question. Problem 4. This is the one that most people thought was the most difficult, which is fair. I think it's probably one of the harder ones. So if we go and think it through, so my story in terms of my energy here is I convert chemical energy into thermal energy. The combination of the two O's into O2 releases energy, which goes into raising the temperature of the gas, increasing its thermal energy. So when I translate that, I start with some UChem, and I also have some thermal energy at the beginning, and I end with more thermal energy at the end. In terms of the UChem, well, that's given in the problem, so we know straight what that is. If I put my definitions in to this problem, so the UChem I can just sort of leave because I know what that's going to be. The thermal energy is the total energy of the total kinetic energy of all the molecules in the system. So that's the number of molecules times the average. And at the end, the number times the average. Going a little bit further, thinking about what the average kinetic energy is. So average kinetic energy is the number of degrees of freedom over 2, kb times the temperature. The number of degrees of freedom over 2 at the end, kb times the temperature. I want to know the final temperature, so I'm going to start doing some algebra here. The easiest way probably to do that, there are a couple of different approaches. There are always multiple approaches for algebra. So you might have done it a different way, which is totally fine. But I'm going to take this whole thing and move it over to the right-hand side. Oops, that should be an F. I can factor out the KB and the 2. Here. NF, number of degrees of freedom at the end. NI, number of degrees of freedom initially, TI. Now, the big N is the number of particles. So at the end, I have 2 moles, which is 2 times Avogadro's number. And initially, I only have 1 mole. which allows me to pull the number of degrees of freedom out. Again, there are multiple, Avogadro's number out. And I can multiply that to the other side. And at this point, I think I'm going to go ahead and put my numbers in. 495 times 10 to the third. We know what Avogadro's number and KB are. If you multiply them together, you get R. Might have just calculated out. That's okay. 2, the number of degrees of freedom at the end is 5. The number of degrees of freedom at the beginning is 3. We also know that my initial temperature, and you all had different numbers here, was 350 K. If you go and crunch all that out, I get 24,175 Kelvin. Very, very hot if all that energy gets used. The part B was all about telling me the story of what's going to happen here. So the change in chemical energy is negative. I'm losing chemical energy here, right? I'm going from single atoms to a bonded state. That's always a reduction in chemical energy. This is something that not only did we talk about in class, but was in your homework as well. And the heat in this case was 0, because heat is transfer of energy with the environment. And there is none of that here. It in fact says no energy escapes to the environment explicitly in the problem, right? So with regards to what happened in class, this is very much a variation on a series of problems we did in class. So there was the syringe where I pushed on the plunger and set the cotton on fire, right? In that example, I'm using work to result in a change in temperature. Then we did the can crush, right? And in that problem, there is both work from the air crushing the can and heat. As the steam cools, heat leaves the can and the temperature falls. Also, the argon problem we did do in class. It was also a next time problem from day 2 to day 3, but we did also do it in class. In this case, we used heat to raise the temperature of a problem. And I even on day 3, slide 7, summarized how all of these are very, very similar. In all cases, we have a gas, and there's some sort of energy that causes the temperature to change. In the case of the syringe, it was work. In the case of the argon box, it was heat. In the case of the can crush, it is both. In the case of this problem, it was chemical energy. So you can see how this is very much a variation on these problems that we did on day 2 and day 3 of Unit 2, right there at the beginning. And then since it had been a while, I returned to this idea on day 5 with regards to the rocket problem, right? So the rocket problem was very much this problem with an additional twist. So the rocket problem was a little beyond what I put on the exam, because the rocket did have this additional twist of, there was the kinetic energy of the rocket to take into account. But it still was a very similar problem, and it was just returning and reviewing the material from day 2 and day 3 of Unit 2. Problem 5 was, can you write math? Right? This is very much what this problem was about. The goal was to understand, give me a mathematical representation for what G is. Where does G, this 9.8 number that we've been using this whole time, where does it come from? Well, in the problem, it says that G depends upon the mass of whatever celestial body you're on, Earth or whatever, and then and more mass, the larger the pull. The radius, it also depends upon the radius of the celestial body on which you were standing. The larger the radius, the smaller the pull. If that's going to be true, I need R to be in the denominator. And since this is the more important quantity, it is going to be R squared. So this is, in fact, the equation that gives you G. If you want to turn it into an actual inequality, just out of curiosity, for your own education, there's a constant annoyingly called big G that's also involved, just a constant of the universe, like the speed of light or something. And that's the true equation. And if you go and put in, this constant, 6.67 times 10 to the minus 11, it's a constant just like the Boltzmann constant or the speed of light or any of these sorts of things. You put in the mass of the Earth, 6 times 10 to the 24th, and you put in the radius of the Earth, 6 times 10 to the 6th meters, and you square it and you crunch all that out. 9.8 newtons per kilogram is, in fact, very much what is your result. So it does work. This is something we practiced a lot in class. We started when we did mathematical representation of entropy, and then I sort of built on it here with this cylinder problem. There was a next time problem where I asked you to come up with the mathematical representation for the volume of a cylinder. We did temperature, we did work, we did a couple of different types of energy. All of these different things, we're practicing our ability to take conceptual information we had and convert it, to translate it into this language of mathematics that we use in science, not just physics, but in all of science. The next problem was problem 6 here. So the first question is, are these macrostates or microstates? Unit 1 quiz problem 4 was exactly this. And then we also reviewed it in class on day 5, slide 10, slide 21, day 6, slide 11, slide 14 on day 7, right? These are very much distinct macrostates, not different microstates. So then we went on to what is the W for the configuration of the two free atoms like this. So this is once again another sort of combinatoric type problem. You're just counting combinations like this, like we did on day 6, slide 11 with the polymer and the oil and the sun and these little flame situations. In all cases, the number of combinations in this case, I have 9 slots, and I'm going to choose to fill 2 of them, and 9 choose 2 is 36. For the single diatomic molecule, well, this was very, very similar to the one we did in class with the 2 sticks in the box. In this case, there was 1 stick in a smaller box. The one we did in class was 3 by 4 with 2 sticks. This is 3 by 3 with only 1 stick in it. And so we can go and straight count the number of combinations. So we can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so for the last part, which has more entropy? Well, we knew part C was 36. So the pair of individual atoms is going to be more entropy. And even if you couldn't actually calculate this, you could probably start thinking about how many combinations there were going to be for the two individual atoms compared to the second one, right? Even if you couldn't do the 9 choose 2 for part C, you can still probably get this, because with this atom here in the corner, there are 8 slots for this other one. 1, 2, 3, 4, 5, 6, 7, 8, right? And then same for this other configuration. Put this one sort of down here in the corner, and you get another 1, 2, 3, 4, 5, 6, 7, 8 configurations. And that already is 16, which is more than 12. So even if you couldn't actually do the combinations, you just were counting sort of things out, you still very much could have gotten E. That's very much a design principle I use in my exams. I try not to make things cascade so that if you miss C, you're completely messed up for E. No, I very much try to make it so that you can get parts without the preceding. Problem 7 was the other problem that folks found to be a little challenging. So once again, we'll solve it out. We have our story. Heat comes in from the flame, and some of that energy goes into gravitational potential energy of the box. And the rest of it goes into changing the thermal energy of the gas. So that's our story here. If we translate that into mathematics, we can say that, okay, I start with some thermal energy, and then I add some heat to it, and that becomes thermal energy at the end and some gravitational potential energy. Could have also gotten there completely equivalent, completely the same, by writing our principle explicitly, and then putting in your pieces, E therm final minus E therm initial. I also have this UG, and then the heat, right? And saying, okay, I don't need to worry about any work. I've already got the gravitational effect taken into account by my gravitational potential energy. You see that these two equations are mathematically equivalent, so it doesn't matter which approach you took. So for sort of the first part here, what is the change in height? This is maybe the easier part, because I told you that the gravitational potential energy increases by 24 joules. So this is a very straight application. If you know what gravitational potential energy is, MGH, then you say, okay, 24 joules is 7 kilograms, 9.8 newtons per kilogram times my height. You solve for your height, and you get a change of 0.3498. For the second part, we don't even have to do any math. We can see that I have almost 700 joules of energy coming in as heat, 24 joules going out, which means the rest of that energy's got to go somewhere. Where's it going to go? It's going to change the thermal energy of the gas, and since nothing else changes, a change in thermal energy will cause the speed to increase. Thermal energy is related to kinetic energy. Kinetic energy is related to speed. Now, to solve out the last part, we'll just continue with what we were doing and add our definitions in. So E therm, number times the average. We have our heat. We have our number times our average. And we have MGHF. We could either use MGHF or we could just leave it as UG, since again, we know what UG is. It's 24 joules. So we can just use that as is. I want to know the change in the temperature of the gas. So let's go and convert our average kinetic energies into temperatures. The number of degrees of freedom over 2 kb Ti plus Q is the number of atoms at the end, number of degrees of freedom over 2 kb Tf plus Ug. For algebra, I'm going to move this to this side and the Ug over to here. So I get Q minus Ug is equal to the number at the end, number of degrees of freedom at the end over 2 kb Tf, number at the beginning, number of degrees of freedom over 2 kb Ti. I'm going to do the factoring trick we mentioned quite a few times in class. It's really beneficial here. Since NF and NI are the same, in this case, the number of moles of gas doesn't change. I can just pull that out. The number of degrees of freedom doesn't change in this problem. So we can pull that out. We can pull the KB out. And that leaves us with our temperature change that we actually want. Rearranging just a few things, we multiply across Q Ug. That's going to be the number of molecules on the bottom, the number of degrees of freedom, and Kb. That gives me my temperature change. So my temperature change, now I can go and put some numbers into this thing. We have this, 699.55 joules minus the 24 joules over how many atoms do I have? I have 2 moles times Avogadro's number. And the number of degrees of freedom was given in the problem is 7. And go ahead and crunch all that out, and I get 11.607 Kelvin. What would have prepared you for class? This is pretty similar to the other oxygen problem in terms of what prepares you, right? This is very, we had the fire syringe, but the one that's really relevant here is the crush-a-can, right? The crush-a-can, we had the can crush and heat go out. In this case, we basically have the reverse. The can is expanding and heat is going in. So this is just the can crush run backwards, effectively. So instead of cooling and collapsing, it is in fact being heated and expanding. The argon, again, very similar with regards to the temperature difference, right? Energy causing a temperature change. Again, the similarities between these problems explicitly discussed on Unit 2, Day 3, Slide 7. And the rocket, again, is probably your best bet on Unit 2, Day 5, Slides 11 through 13. Okay. Problem 8. This is our two little magnet problem. For part B, this is the diffusion problem, the dye diffusion problem, with simplified to be only 2 atoms instead of the 4 we did in class on day 6, slide 7 in general. So instead of thinking about the atoms being on the left or being on the right, we're now thinking about the atoms pointing up or pointing down. It's almost the exact same problem. So how many are they going to be aligned? Well, we have 2 combinations here. I'm just going to count them because I think that that's actually the easiest. I could have them both like this, both pointing with their north poles down, or I could have south, south, north, north. So we see that there are 4 combinations. They are aligned half the time. So you could have also done some NCR type of stuff, but it's small enough that I think it's actually relatively straightforward to just count them all. What happens when you increase the number of atoms? As we increase the number of atoms, the probability of seeing them all perfectly aligned, just like the probability of seeing them all on one side, will decrease as a function of increasing the number of atoms, but it will never reach exactly 0. I mean, it's going to get very close, as we can see right here, right? When we got to 100 atoms, it was 10 to the minus 30, but it's never quite going to be 0. So this problem was very much a version of the dye diffusion problem that we spent a couple of days studying right at the beginning of Unit 1, Day 7. Problem 9. This is our drop a rock through the air type of problem. So let's think about our story. I start this situation with gravitational potential energy because I am dropped. So I start with no speed. As I fall, I lose some energy to the air. The rest of the energy is converted to kinetic energy upon impact. So when I translate it, we have E final minus E initial. I'm going to start with my principle very explicitly here. We don't have any heat to speak of, but we do have work. There is a force of air resistance acting on the rock as it falls. So we definitely have some work. At the end, we only have kinetic. At the beginning, we only have gravitational, and that becomes our work. So when I put my definitions in, we have 1/2 mvf squared minus mghi is fd cosine theta. And so from even here, again, I'm breaking it up to give the partial credit for all of this work with these drop-down menus. We can see that the gravitational potential energy is decreasing while the kinetic energy is increasing, right? I started from rest and ended as I fell, but these two things are not going to be equal to each other because of this W, right? If I sort of rearrange it, the final kinetic energy is the two together. And remembering that that's a negative number, energy is being lost, the change in gravitational potential energy is going to be larger. So once again, this is all of these first three questions are about understanding the story of what's going on with regards to our energy. And now I can go and do some algebra here. I'm solving for F, so 1/2 mvf squared minus mghi all over d cosine theta is going to be F. Put some numbers into this equation now. We have a 1/2. The mass of the stone is 5. The final speed for me was 4.45 squared. The mass is 5, 9.8. My initial height was 5 meters. You can't really see it because it's under my picture, but believe me. And just like a problem we did in class, the height it falls and the distance it travels have to be the same. So that's also going to be 5 meters. And then it is cosine of 180 degrees, which I can see because if this is my rock, it is moving this way, and the force is going to be opposing the motion. The air resistance is opposing the motion, just like friction does. And so we see this 180 degree difference between the two. So just like in these two problems with our sled, our penguin on our sled going across the rough spot here, right? The energy was being lost. There was a 180 degree. There was also a unit 2, day 4 to day 5 next time problem, which was also very, very similar to this problem. Finally, we come to problem 10. So for problem 10, I'm going to start with my story. I start with some elastic potential energy, the compressed spring, and I am converting it to kinetic energy, is what I'm doing. So if I translate that into mathematics, it's 1/2 kxi squared, 1/2 mvf squared. The halves cancel, not that it over much matters, but you can see that x and v are to the same power, right? I've got kxi squared is mvf squared, which maybe it's easier if you take a square root of both sides. Then you've got xi square root of k is vf square root of m. And so if x doubles, speed will double. Very similar to these problems we did in class, where I dropped a ball from a height, and we said, how does the speed change with regards to height on day 4, slide 7. And then we did another one there on day 5, slide 4, where we looked at the work needed to stop a car with the Mythbusters episodes, right? So this is us going through the exam sort of piece by piece. Hopefully you now have a clearer grasp on not only how all the different parts of the course fit together, but also how each problem we did in class was very much preparing you for the problems that were on the exam. I mean, some of them are direct variations, right? The flame with the rising box is a direct running backwards of the can crush. The arm, we did the full arm, and as a next time problem, you had the full arm, and then on the exam, I gave you just the forearm. So some of them are direct, and some of them are a little bit maybe less obvious in how they connect, but hopefully this video has elucidated those connections for you. I'd like to end with some summary stats on the exam, and sort of thinking about how it broke down. So this is based upon the points on the exam. So basically everything you could answer was worth the same, 4 points. If you break it down, there were 45.8% of the points came from what I would consider to be conceptual questions. So things where you're looking at the story of the energy and telling me, you know, what goes up, what goes down, what's relevant in this energy story, and what's not. All of those types of questions were relevant. So for example, you know, this one, if you could read the story, you could get this latter part was very explicitly about the story. So that was, like I said, 45.8% of the questions. Another 41.7% of them required you to actually do some sort of mathematics. And then there were reading and writing math problems that were 12.5% of the points, 1/8 of the points. For those, I'm sort of thinking about this one, right? There was some computation there, but it was really more about reading and interpreting the result. We also had the this problem here with regards to, you know, do you know how entropy works? And of course, most explicitly, we had the problem where you had to tell me the mathematical representation for gravity. So those were the three that most came to mind when in this reading and writing mathematics part of the exam. And on the right there, you have the breakdown of the problems we did in class. So there are about 65 problems in the slides. This includes the next times. You know, you might get slightly different numbers depending upon how you count them, but I got 65 when I did the counting. And of those, it was about 40% conceptual and 40% calculation. So about an even split, conceptual versus calculational problems. And you can see that same breakdown on the exam. It's an even split in class and a close as I could get to an even split on the exam. And with regards to reading and writing math, we did more practice on that in class relative to what was on the exam. But I did that intentionally because I think that that's a skill that probably a lot of folks are less familiar with, less comfortable with. So I wanted to make sure that we had plenty of practice for those types of problems in class so that you would be ready for what we did on the exam. And also so that you would be more comfortable with the mathematical representations of these different ideas like kinetic energy and entropy and all those types of things, right? I want you to be familiar with those mathematical representations and understand how they connect to the conceptual ideas that we're talking about. So hopefully this is sort of clarified where the exam's coming from, how it matches to what we did in class. Like I said at the beginning, if you're watching this and you're still thinking to yourself, I do not see how this stuff connects, I don't know how to be successful in this format, anything like that, please, 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 please come to a Brock Talk. And if those don't work, make an appointment. I'm happy to talk to you so that we can come up with something that will work for you. This concludes this video.